My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good afternoon to all here in Bangladesh, and a very good morning to all those who are watching this program live from UK. It's our 96th International Physics webinar. So hope you are well and safe from Corona pandemic. So all we know that we are staying in a Corona pandemic situation. All the institutions have been shut down since March 2020 due to Corona pandemic. So we cannot continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology, has started its online program, including online classes and international physics webinar. And we have successfully completed our 95th International Physics webinar. Today it's our 96th International Physics webinar. And we are trying to adjust with this new normal situation. And today is very important day for our department. Today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Institute of Astrophysics, University of Gottingen, uh, Germany, in astrophysics. And we have with us here today Dr. David J. Marsh, Professor, Department of Physics, Institute of for Astrophysics, University of Gottingen, Germany, and he has already connected with us. So I'd like to welcome our speaker. So good afternoon, sir, and welcome to our International Physics webinar, and welcome to our university and country through online. So this may be your first any collaboration talk and any webinar with any Bangladeshi university, isn't it, sir?
Yeah, it is.
Oh, great. Thanks for accepting our invitation. So for those who are new, I'd like to inform that we'd like to divide our webinar into three parts. First of all, we'll introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion time. In that time, anybody can join with us, and you can ask question by commenting. So I think you have already come to know the title of this today's international webinar, and our title is the evidence for dark matter. Very exciting topic. And our speaker is Dr. David J. Marsh, Professor, Department of Physics, Institute for Physics, University of Gottingen, Germany. So we can see his academic and professional background. So Dr. Marsh was born in Liverpool and attended Edinburgh University. He did his PhD in Oxford on theoretical particle physics and cosmology thesis, the string Exivers and cosmology. David is currently a fellow in Germany, and outside of physics, he has been sketchboarding for more than 20 years and loves literature and music. So astrophysical and cosmological observation across a vast range of scale, from dwarf galaxies to the size of the visible universe, indicate that dark matter drives structure formation. There is no known particle that can account for dark matter. Modification of gravity cannot self-consistently explain the observation either. Thus, they require a new type of particle or particles or some radically new physical laws and processes to explain the observation. His research is all about trying to identify this new physics using astrophysics and cosmology. His favorite dark matter models come under the class of particle known as axions, and he's interested in all the physics related to the broad topics, from string theory to the large-scale structure of the universe, from quantum chromodynamics to gravitational microlensing, and from instantons to nuclear magnetic resonance. A large part of his work at Gottingen will be the collaboration with Professor Jens Niemeyer, and will focus on a numerical simulation of ultra-light axions and fuzzy dark matter. So the lightest possible dark matter candidates and frontier of our knowledge of structure formation. You can see his educational and work information. So very recently, he has just been awarded an Ernest Rutherford Fellowship at King's College London, and will be moving there in March next year. And you can see he has completed his master's degree in mathematics from University of Edinburgh, and DPhil, a theoretical physics, that means PhD, Oxford University, and postdoctoral researcher in Premier Institute of Theoretical Physics and also postdoc in Royal Astronomical Society, and also a fellow in University of Gottingen, and now he's currently working as a professor at University of Gottingen. And we can see his teaching experience and lecture. So this is his seminar in different organization, and this is award. So this is Inspire Help ID. So thanks all for all of your patience. Now it's time to go to our speaker. So thanks again, sir, for accepting our invitation. It's your time. You can start your session, sir.
Great, thank you, Pretam. Thanks for
It's
the
my pleasure.
invitation. It's very nice to be giving a seminar to people in Bangladesh. As you said, I've never given a seminar at Bangladeshi University before, so new experience for me. And I hope that when the pandemic is over, maybe I can visit you in person sometime. That would be really nice.
Yeah, of course, I will definitely invite you. It will be a great pleasure.
Very happy to come and maybe meet some of the participants. Okay, so I'm going to be telling you two things in the seminar today. I'm going to tell you first about the evidence for dark matter. We'll do that for about 40 minutes or so. And then I'll switch over to tell you about my favorite dark matter particle and how you can find it, about axions. But first of all, the evidence. So we observe the universe with light. And this is how we know almost everything we know about the universe. So we need an introduction first to light. Remember that we describe light as an electromagnetic wave. That wave has a wavelength and it also has a frequency. If we have a short wavelength, we have high energy, that's here, and high frequency. If we have a long wavelength, we have low energy and low frequency. And visible light sits in the middle. Also, the temperature of an object is related to its energy, and the energy reflects the frequency of light emitted. So if something is hot, it's going to be giving off high energy light. It's going to be giving off, say, X-rays, whereas if something is cold, it's going to be giving off low energy radiation, for example, in the microwave or the radio. With that in mind, we can talk about our different pieces of evidence for dark matter. And the first piece that I want to tell you about is the evidence for dark matter in galaxy clusters. So this is an image of a galaxy cluster, and all of the objects in this image, apart from the bright foreground stars, are all galaxies. So when we normally look up at the sky, we see stars, but and all the stars that we see, in fact, are stars in the Milky Way for the most part. You could just about see Andromeda, I think. But when we look at the sky with very powerful telescopes, we see galaxies further away than the Milky Way, and the galaxies cluster together and orbit each other in things known as galaxy clusters. And this is what one such galaxy cluster looks like. So the evidence for dark matter in galaxy clusters was really some of the first evidence that we had, and it came from an astronomer called Fritz Zwicky. And the evidence relies on the concept of equilibrium. So when we normally think of equilibrium, we think of a balance of scales. And we know that, for example, if you put 1 kilogram on one side of your scales and anything else on the other side, if the scales are balanced, you know that the other thing, whatever it is, whatever it's made of, has to weigh 1 kilogram. In a cluster of galaxies, there is a balance as well. And that equilibrium is a balance between the mass in the galaxy and the velocity of the galaxy, the mass of the cluster and the velocity of the galaxies that are orbiting in the cluster. And what we observe is the galaxy velocities. So we observe this from the redshift of the light. We observe the galaxies and they're moving. This tells us the galaxy velocities. And the balance on the other side of the scales allows us to infer the total mass of the cluster. So if we see galaxies moving at a certain velocity, we can infer from what's called virial equilibrium what the total mass in the whole cluster has to be. And the mass that we see, the mass that's required to balance the scales, is more than the total mass of all the stars in all the galaxies in that cluster. So this leads us to infer that there has to be something in the cluster that is invisible and dark. And this is what was done by Fritz Zwicky in 1933. Fritz Zwicky, he looks quite fun, doesn't he? This image of him is very famous. He observed a cluster called the Coma cluster, which is the one here on the right-hand side. He counted up the velocities of all the galaxies. He counted up all the stars. He worked out that much more mass was in the stars to give rise to observed velocities in the Coma cluster. Times have moved on since 1933, and we now see clusters in much more detail than Zwicky did. So what is the visible stuff in clusters? The visible stuff that we actually see the velocities of is gas. And we know from the classic kinetic theory of gases that the kinetic energy of the gas gives rise to the pressure of the gas on the walls of the box, and is specified by the temperature of the gas. And temperature is a measure of the kinetic energy. So the temperature gives the velocity of the gas particles, and that gives rise to the pressure on the walls of the cube in this diagram. And because there is an equilibrium between the pressure, the effective outward pressure of the gas, pressure acts outward, velocities want to move outwards, velocity dispersion wants the gas to expand, whereas the gravity is holding the gas in. And this equilibrium means that there is a typical temperature for gas in a cluster based on the total mass that is holding that together. So how does that work? Clusters are very heavy. A cluster of galaxies, if you think a typical galaxy has about the mass of 10 to 12 solar masses, clusters are very many galaxies, so they're very, very heavy. So the equilibrium that you require to make the gas be bound inside requires the gas to be very hot and thus ionized. And if a gas is ionized, we have an interaction between the electrons in the gas and the ions in the gas that causes the gas to give off radiation, and the energy of that radiation will be linked to the typical temperature of the gas, and thus the total mass of the cluster. So this is what happens. We have an ionized gas, and the electric force, the Coulomb force between the protons and the electrons, causes the electrons to change direction. When something changes direction, it's accelerating, and that acceleration causes the electron to give off a type of radiation, which is Bremsstrahlung. And Bremsstrahlung, I've been living in Germany now for a few years, I know what this means. It is German for braking radiation. So Brem to break, Strahlung radiation. So radiation given off due to something slowing down. So the electron slows down and gives off some energy. And that energy is related to the typical energy that the electrons and the protons have, which is the typical kinetic energy, which is given by the temperature. So if something is hot, it has a lot of energy. This energy that we give off will be in the X-ray. So high energy, high frequency, short wavelength X-rays. So that's how we observe gas in clusters. We make a telescope that sees X-rays. Instead of seeing visible light, the telescope picks up X-rays, and you pick up those X-rays from the hot gas in the cluster, and from the energy of the X-rays, you infer the temperature of the cluster. So, for example, an X-ray satellite would be a satellite like Chandra. So we can see gas. We can see the X-rays, and we infer there has to be a lot more matter than the total gas in the cluster or the total number of stars in the cluster, and this has to be dark because we can't see it. We can see what dark matter does to light, and we can try and see where it actually is in the cluster. Is there any dark matter? Where is it? And we see that by using something called gravitational lensing. So now the picture is, here's us on the Earth, and here's the cluster that we want to see the dark matter in. If we have a background light, a background source, so a galaxy that's behind the cluster, and behind here means quite a few billion light years behind. The cluster might be, we use a measure of distance in cosmology called redshift, the cosmological redshift. The cluster might be at redshift of, say, 1 or 0.5. Background galaxy could be a redshift as high as 6. So that means that the cluster is, say, a billion light years from us, whereas the galaxy is, some number of billion light years from us, 4 or 5 or something like that. And the light from the galaxy wants to travel in straight lines, but the mass of the cluster in space-time and causes the light to like it was moving through a lens. So if you want to visualize this, and if you take a wine glass has a stem and then a base around base, and that type of lens, shape of lens, is the shape of lens that matter makes when it bends space. And if you place a glass like that on, say, an image in front of you, a piece of paper, you'll see that the image is distorted into rings caused by the light, caused by the lens. Matter does the same thing. And the strength of the lens, the power of the lens, is related to the mass of the stuff that is doing the lensing. So in this case, we would see, instead of just a nice elliptical galaxy, we would see the shape of that galaxy distorted into some sheared shape, into some bent shape by the mass. Here's a nice picture that I found just when I was Googling for images of gravitational lensing. This is a garden, presumably in some kind of a university, and this, and this looks nicely like lensing. So here's the bars going through the garden, are like the rays of light coming from the galaxy. So here's an image of a lensed galaxy cluster, of a galaxy cluster doing lensing, a galaxy cluster lens. So it has this name here, RCS2, blah blah blah. And the cluster, as I said, is a few billion light years away. It's about 5 billion light years away. And this is an image taken by the Hubble Space Telescope. So the yellow images, they're galaxies in the cluster. But then there are these strange arcs, these strange bluish arcs in the image. And these are actually galaxies, but they're galaxies behind the cluster, which have had, as I said, the light coming from them smeared out and lensed by the mass in the cluster, and this leads to them forming these rings. They're called Einstein rings after Einstein. This is general relativity that causes the lensing. And by looking at how much this image has been smeared out, assuming that galaxies, we know they're roughly elliptical, by looking at the amount of shearing that's been done here, you can infer where the mass is in the galaxy cluster and how much of it there is. So now we've got two things which we can use to look at clusters. The first is the hot gas, and the second is the gravitational lensing. And these come together in a famous object called the bullet cluster, which is a very famous piece of evidence for dark matter. So here's the bullet cluster. This is an image of the bullet cluster made in 2006 in this paper by Chloe et al. And let me explain to you what you're seeing in this image. First of all, in the color code, you see the hot gas. So in the color code, you've got blue, red to yellow to white is the X-ray image taken by, I believe, the Chandra telescope. And where there's more gas, the colors are brighter. So we've got lots of gas here and here. And this is why it's called the bullet cluster. It's actually two colliding clusters. And one, the one on the right, has moved through the one on the left. And you can see that it's moved through because it forms this bow shock on the other side. And that's where it gets the name the bullet cluster. So it's two colliding clusters, and the one on the right has recently, in cosmological terms, probably 1 billion years ago, moved through the one on the left. So but then there's another part of this image, and that's shown by the green contours. The green contours are the estimation for the location for where the mass in the cluster is from lensing of galaxies behind it. So there's an image in the optical, like the one we saw before, of the galaxies in the cluster. Then behind it, there are some other galaxies. The images of them have been sheared and moved around by gravitational lensing. And from that, you can infer where the mass is, and that's the green contours. So this is just like contours on an ordinary map. When we used to have paper maps and not Google Maps, you could see contours, and the contours get closer together as you move up, say, a mountain. And the same is true here. So we have two peaks in the mass. Now, the peaks of the mass are not at the peaks of the gas. And this is what tells us that there is dark matter. The total mass is peaked over here, whereas the gas is peaked over here. So the mass in this cluster is not where the visible stuff is. Gas is what makes up most of the mass in clusters, not the galaxies themselves. And furthermore, the gas has kind of lagged behind the motion of the matter. The two bits of matter in the cluster just moved straight through each other, whereas the gas, whereas the gas got dragged behind. That tells us something about dark matter. That tells us that it doesn't behave like ordinary matter, that it doesn't interact with itself, that it doesn't have pressure. So we've learned that there is dark matter in this bullet cluster in a very striking image. And we've also learned that dark matter doesn't interact with itself very strongly. Okay, so that's evidence one, dark matter in clusters. The second piece of evidence I want to give you for dark matter is the evidence for dark matter in galaxies, inside galaxies, so coming on all different scales. So this is an image of a galaxy called the Sombrero Galaxy. And you can see in it that the matter lives in a disk. Okay, so how do we get evidence for dark matter from galaxies? We get it from something called a rotation curve. So what's a rotation curve? So imagine taking a yo-yo on a piece of string and swinging it around your head. If you swing it slowly, you don't have to pull on the string very hard. However, if you want to spin it faster, you have to pull hard on the string. So the force that you require to make something rotate faster is larger. This is the famous, this is just ordinary centripetal acceleration. The force is v squared over r. So we can do the same thing with gravity. If a star in a galaxy is moving very quickly, then the gravitational force has to be large. So how do we measure how do we use this to measure the mass in a galaxy? So this was done very famously in 1970 by an astronomer called Vera Rubin and her collaborator Ford. So here's Vera Rubin in the 70s. You can tell by the pattern on her clothes and the style of her glasses that it's 1970s. And what she's doing here is she's inspecting an image of the galaxy M31. And this is the data that Rubin took from her paper in 1970. So what she did is she knew the distance of, again, a type of gas, neutral hydrogen, from the center of a galaxy. And she measured the velocity of rotation of that gas. Now, in galaxies aren't as massive as clusters, so the gas is colder, so it's not ionized. It's cold, so the energy scales of the gas are much lower than the gas in clusters. That means that to make an observation of the gas in a galaxy, you don't use an X-ray telescope, you use a radio telescope. The energy is lower, so it's down there in the radio frequencies at long wavelength. So what Vera Rubin did is she had radio observations of this galaxy M31, Andromeda, and measured the velocity as a function of distance. So the distance is measured in minutes of arc, and the velocity is measured in, what's that, kilometers per second. Okay, so typical velocity of the gas, 200 kilometers per second, and then the distance on the top y-axis given in kiloparsecs. A parsec is about 3 light years. So the size, so the distances that she's measuring are up to, about 100 light years across in this galaxy. And the rotation curve remains high. The rotational velocity of the gas is large, even at very large distances from the center of the galaxy where all the stars are. That's why she had to use this gas. You can see stars in the inner parts of galaxies, but the gas in the galaxy, so that is the stars in the inner part, the gas extends much further out. The gas doesn't make up very much mass in a galaxy, but it's still rotating very quickly. So here's a modern rotation curve. This is the rotation curve M33. And here again, you see much nicer measurements because it's made with a more modern telescope. And the stars rotate like this. Now the stars make up most of the mass in a galaxy. So as you move further away, the gravitational force from the stars gets less. So you would expect that objects further away from the center of the galaxy are rotating at a slower speed. However, when you measure this neutral hydrogen, the 21 centimeter emission line of neutral hydrogen, you see that the neutral hydrogen continues to have a large rotational velocity. And this leads us to believe that there has to be a whole lot more matter that lives also in the outer parts of the galaxy, in what's called the dark matter halo, in order to create the required gravitational force to pull on the neutral hydrogen and make it rotate at these speeds. So this is now a cartoon of this apparent dark matter halo and what we think it might look like in our own Milky Way. So here is the disk and the spiral arms of the Milky Way. The spiral arms that you can see if you look up at the night sky and you're somewhere that's far from any light pollution. And here are lots of satellite galaxies of the Milky Way, things called Fornax and Sculptor and Draco, etc. And we think that they all live out in this big thing called a dark matter halo, where the mass of dark matter around the Milky Way extends for a very large distance. So this evidence for dark matter is significant because it tells us that dark matter isn't just out there in clusters, it's here. And we're here. The sun is in one of the spiral arms of the Milky Way, 8 kiloparsecs from the galactic center. And we think there's dark matter there even, pulling on the gas to make it rotate quickly. And we actually know from measurements of the rotation curve of the Milky Way how much dark matter there is right here on Earth at all times in this room. And this is the density of the dark matter on Earth. So it's about the mass of, the density of dark matter is equivalent to the mass of 1 proton in every centimeter cubed. So remember, a centimeter cubed is a milliliter. So if you have a 500 milliliter bottle of water, the mass of dark matter approximately in there is about 500 protons. Now compare that to the 10 to the power 23 Avogadro's number of protons that are in the water. The density of dark matter on Earth is very low, but we know how much there is, and so you can try and detect it. If you find imagining 1 proton in a milliliter or 500 in a bottle hard to imagine, I'll come back to an analogy for that in a minute. But yeah, the Milky Way rotation curve tells us the density of dark matter on Earth. And yeah, as I said, if you find 1 proton in a centimeter cubed hard to imagine, that's equivalent to the mass of about 1 squirrel, a squirrel worth of total mass, if you took the squirrel and spread it out through the contents of the entire Earth. So squirrels are small animals that we have. That I don't know if you have squirrels in Bangladesh, but they're small animals about this big. If you took a squirrel and you smashed him up and spread his mass through the entire volume of the entire Earth, not just over the surface, but throughout the whole centre, that's about the total mass of dark matter that there is at any one time passing through the Earth. Now, we know not just the amount of dark matter that there is on Earth, but also our relative velocity with respect to it. The dark matter, we can think of the rest frame of the dark matter, and the sun is moving with respect to that rest frame as it rotates around the centre of the Milky Way. And it's rotating at 200 kilometers per second. And we're moving roughly in the direction of the constellation Cygnus, that's the Swan constellation. And so at all times, there's a wind of dark matter effectively moving through the Earth. So we know the flux and the wind rate of the dark matter and its density. And this is key in efforts to try and detect it. And I'll talk about some of those in the second half of the lecture. The final piece of evidence for dark matter that I want to tell you is an evidence for dark matter on the scale of the cosmos itself, and the scale of the whole universe. And this is also an excuse for me to show you one of my favourite images in all of astronomy. This is the Sloan Digital Sky Survey, SDSS, map of galaxies. And so the stripes on this are just the way they make the observations, and this is looking north on the right and looking south on the left. And this image might look like just a load of static to you. You know, the kind of thing that is on your television if it's not plugged into an aerial. But it's not static. Every pixel on this image is a galaxy. So there's around, I think, 200 million galaxies in the Sloan Sky Survey, and that is just a small fraction of the volume of the visible universe that they surveyed. And if you look even more closely at this image, you see patterns in it, kind of web-like structures moving around here. And that's not your eyes playing tricks on you. That's real structure, real statistically defined structure in the map. And this is what we can use to try and find evidence for dark matter on these huge, huge scales. So, how do we get evidence for dark matter on the largest scales? We actually use an idea like I'm showing you here. So this is an image of the surface of the sun. And the surface of the sun, in the sun, hydrogen is broken up into protons and electrons. And the sun is very hot. Now, we think that the universe, when it was very young, was also very hot, and it was something like the sun. This is important for two reasons. The sun, we can't see through the sun. Why can't we see through the sun? Because it's a hot plasma, and light can't get through that plasma. When light tries to move through a plasma, it scatters off the protons and electrons, and it doesn't get through. So if the universe was very hot, it was like this at early times. But the light that comes from the sun to us is invisible because the sun is hot. But if you stretch that out over time, that light would cool down as it goes further and further. And the light coming to us from the early universe should be shifted down from there into the radio. So, okay, I'm going to explain what I mean here. So just like inside the sun, the universe burns hydrogen into helium. So the sun turns hydrogen into helium via nuclear fusion. We know that the early universe was something like the inside of the sun because of a theory called Big Bang nucleosynthesis. And by observing the ratio of hydrogen to helium in the universe as a whole, by measuring how much hydrogen there is and how much helium there is and counting it, we can work out the density that the plasma of the early universe had to have. So we know how the sun works, and we know how quickly hydrogen burns into helium. We can do the same thing for the whole universe. If we know how much hydrogen there is and how much helium there is, we know what the density of the plasma should have been. And this is important because we can use our idea of equilibrium again. So we know how much stuff there was, how much plasma there was in the very early universe. Okay, and we use Einstein's other equation. So not E equals mc squared, but this equation, G mu nu equals 8 pi G Newton T mu nu. So this is the central equation of general relativity if you've never seen it. And I just want to show you it because you can write it down. All of general relativity is written down in one line here. But this is just the E equals mc squared of general relativity. And it says that geometry equals matter. So on the left-hand side, we have geometry, something called the Einstein tensor. And on the right-hand side, we have matter, T mu nu, something called the energy momentum tensor. So why is this important? How does this connect to the idea that the early universe was hot like the sun and that we know the density of the plasma? Well, because it relates to cosmic geometry. So if you've got lots of stuff, lots of matter on the right-hand side, you get lots of geometry, lots of curvature. If you've got not very much matter on the right-hand side, you get not very much geometry on the left-hand side, not very much curvature, or even negative curvature. When you have just the right amount of stuff, you get something that's flat. So that's illustrated in this image here. So something that's strongly positively curved is something like the sphere. And on the surface of the sphere, angles of a triangle add up to more than 180 degrees. If you have something that's negatively curved, you have something like a saddle, and then the angles of a triangle add up to less than 180 degrees. And if you have just the right amount of stuff, you have something that's flat, that has Euclidean geometry. Angles of a triangle add up to 180 degrees. So we can make measurements and try and determine the geometry of the universe. We do this by basically doing the equivalent of making big triangles in the sky and looking at whether the angles in them add up to 180 degrees. And we find that they do by many different measurements. And these imply that the universe is flat. But we know how much normal stuff there is in the universe. We know the total density of the plasma in the early universe from the ratio of hydrogen to helium. And that's not enough to make the universe flat. So there has to be more stuff. There has to be more stuff than just the plasma in order to make the universe flat and consistent with what we observe. So to gain an idea of balancing, of equilibrium, like right from the beginning, but now it's an equilibrium between matter and curvature. We can do even better than that observation though, by trying to look for evidence of this hot phase in the early universe. So if the universe was a plasma at early times, it was giving off, as I said, light like the sun, hot energy. It would have originally been in the X-ray. However, as the universe expands, that radiation cools, and eventually the universe becomes neutral and we can start to see through it. That's why we can look out into space. And the energy then that was given off when it was hot has now cooled and gone down from the X-ray energy into the radio again, into the microwave. And we can try and observe it in the cosmic microwave background. And so here is an image of the first people, Penzias and Wilson, to discover this cosmic microwave background, and the telescope that they used to do it, which was the radio telescope at Bell Labs near Princeton in the United States. And they weren't expecting to look for the cosmic microwave background. And when they saw it, they just saw a background fuzz in all of their observations. And they thought that this can't be right. There can't be microwave radiation coming uniformly from everywhere on the sky. So they thought it might have been pigeon poo. And so they tried to track the pigeons. And this is a picture of the trap that they used to try and trap the pigeons. And it's you can see it in the Smithsonian Museum in Washington in the United States. And I've been there and I've seen the pigeon trap, but this is not my picture. So they tried to trap the pigeons, and there were no pigeons. There was a cosmic microwave background. And since 1967, when Penzias and Wilson discovered it, we've been observing this cosmic microwave background for a long time. And here are three images of it. So this is now the projection of the whole sky. This is a picture of the entire universe taken in the microwave, and it's an image taken by the COBE satellite in '92, the WMAP satellite in 2003, and the Planck satellite in 2013. And what the image shows is the variations in the temperature of the microwave sky with respect to the mean. So the mean temperature is 3 Kelvin or so. That's what Penzias and Wilson determined. But now we measure differences in that temperature across the sky. And the differences are about 1 part in 100,000. So this part of the sky in blue is colder than the part in green by 1/10,000th of a degree about. So very small temperature variations. But again, the patterns in this are not your eyes playing tricks on you. There is structure to the temperature variations. And we use this also to construct evidence for dark matter on the very largest scales. And it's due to a theory that earned Jim Peebles the Nobel Prize last year. So this is Jim Peebles, and he was actually down the road from Penzias and Wilson in Princeton at the time, and he was trying to look for the cosmic microwave background too, with his PhD advisor, Bob Dickey. So how does the cosmic microwave background tell us about evidence for dark matter? So the origin of everything in the universe, we think, is due to, you start off with these small temperature variations in the cosmic microwave background and dark matter. And then if you just let gravity go and solve the equations for how much matter do we think there was based on the ratio of hydrogen to helium versus keeping the universe flat, start off with the fluctuations in the cosmic microwave background and solve the equations for how that evolves. And you can do it on a computer these days, although Jim Peebles did it with pencil and paper. When you start off, but he also pioneered the computer simulations later in the 80s as well. But if you solve then the equations of gravitational instability, and it looks something like this when you do it on a computer, it forms this network of structures. So this is a simulation called the Millennium Simulation, and it forms into these web-like structures. Then you can even nowadays solve the equations with gas as well, the gas that we've seen observations of that Vera Rubin observed in galaxies. And these simulations, like the fire simulation, even lead to formations. This is just a table of galaxies. It's not really the layout in the simulation. These are galaxies that you get in your simulation. So you even get galaxies that look just like the ones we observe, doing just what we expect them to do. So this is all in theory, but it matches the observations, and it only matches the observations if you have the right amount of dark matter. So this is now the observations of the cosmic microwave background, and we take a theory. We have the data on the cosmic microwave background and a theory, and the theory fits the data only if there's the right amount of dark matter. And the theory is gravitational instability from small fluctuations. And the same theory also explains the distribution of galaxies on very large scales. So you can then take the distribution of galaxies, and I said the patterns in here are not your eyes playing tricks on you, and turn them into some data like this on a graph, and the theory goes through the data, and it's the same theory that fits the cosmic microwave background, and it only works if you have a very large amount of dark matter in your theory. So that's all the evidence for dark matter that I want to tell you about. We know about dark matter inside galaxies and on the Earth from observations of rotation curves. We know about dark matter on the scale of clusters of galaxies, between galaxies, from observations of hot gas and gravitational lensing. And we also know that dark matter holds the whole universe together and is responsible for the structures is responsible for the whole formation of structure in the entire universe, going from that hot, dense state into a state now that includes galaxies and human beings. So that's the evidence for dark matter. And this is just the final image I want to show you in this part of the talk. We can actually make, using the cosmic microwave background, an image of all the dark matter in all of the universe, a map of dark matter across the whole universe, using gravitational lensing, but this time of the cosmic microwave background. So this is such a map made by the Planck satellite, the European Space Agency. There's a mask in the middle. We can't do this where we're in our own galaxy, but we can do it across the whole sky. So we know an awful lot about how much dark matter there is and even where it is, but we don't know what it is. So we know it exists, but we don't know what it is. And in the last 15 minutes, I'm going to switch slides and tell you about my favorite theory for dark matter, where dark matter is a wave. So just let me now switch slides. Okay, and switch slides. Okay. So, great. So, the last 15 minutes or 20 minutes or so, I'm going to tell you about what dark matter might be. And I think it might be a wave. So light, we've already seen on the first slide of the last part, light is a wave that we're familiar with. And light is a wave that is described by a wavelength lambda and a frequency f. The other bit of physics that you need to know about for this part of the talk is about natural frequencies. So physical systems have a natural frequency, and this is how antennas work. So this is an image of the Jodrell Bank radio telescope in the United Kingdom, and the way that an antenna works is it has a length scale, and the length scale defines a natural frequency, and the length scale is proportional to 1 over the frequency. And so if you have a big radio telescope, you detect long wavelength radio waves via the resonance, the natural frequency of the telescope, matching up with the frequency of the radio waves. The other bit of physics that we need to think about dark matter waves is quantum mechanics and matter waves. So this is the famous electron the electron double slit experiment that shows that matter also behaves like a wave. So you take your electron gun and you shoot it at a slit, at 2 slits, and the electrons observed on the other side form an interference pattern. And waves form interference patterns and particles don't. So this tells us, oh, that actually matter behaves like a wave. And if it's a wave, we need a wavelength and a frequency. The wavelength of the matter is given to us by the de Broglie wavelength. So here's Mr. de Broglie. And the wavelength of a matter wave is proportional to 1 over its mass. We also need a frequency to describe a matter wave, and that's given to us by Mr. Compton. And Compton tells us that the frequency of a matter wave is proportional to its mass. So now, if we have a particle, we also have a wave. But when do you notice that something is a wave? We notice a particle is a wave when the wavelength is close to the slit size, in this case, if the wavelength of the electron is close to the slit size. Or we can also notice that something is a wave if its frequency is low enough to measure, if we can actually measure the time variation of the wave on a relevant timescale. So if dark matter is a wave, it means that it has a wavelength that is of order the size of something that we're using to observe it, or that it has frequency that is low enough that we can see the time variation of the frequency of the dark matter. So yeah, all particles are waves, but when do we care that dark matter is a wave? When some of these conditions are satisfied. So when is dark matter a wave? So here is a diagram of all the different types of dark matter that you might find from a webcomic called XKCD. And if something is heavy, it has very short wavelength, very high frequency, And we're not going to be able to see that wavelength or that high frequency. But if the dark matter is very low mass particles have long wavelengths and low frequencies, radio frequencies, that you can observe. And so here on the dark matter candidates list, at the top, we're measuring things in 10 to 30 kilograms, that's solar mass, and that's black hole dark matter, which is largely excluded. And right down at the low end, we measure the masses of things in familiar particle physics units. So a GeV, the mass of a proton, typical for something called a neutralino. But at the very lowest masses, this cartoon is accurate. There is a class of particle called an axion. They have masses smaller than an electron volt. So an electron has a mass of a kilo electron volt. So these are milli-electron volts, micro-electron volts, many orders of magnitude lighter than any other type of particle that we know. But if the dark matter is that light, it can have a long wavelength and it can have a low frequency, and we might be able to observe its wave-like nature. So there are a couple of ways that we can do this, and I just want to give you a feel for it. So first of all, if the dark matter has a very long wavelength, its wavelength could be of order the size of a galaxy and could affect the evolution of galaxies. So here's an image from a numerical simulation like the ones that we saw earlier, but now including the idea that dark matter has a wavelength. And this was done by a graduate student, Jan Belmont. So here's the web-like structure that we saw already, but Jan has now zoomed in to the inside of a galaxy where he simulated a dark matter with a wavelength. And you can see in the inset the interference pattern that this dark matter forms inside a galaxy. And here is a video. So now you see the dark matter having a frequency of variation in the waves and also a typical wavelength. And these types of effects we might be able to observe if the wavelength of the dark matter is of order the size of a galaxy, which is, as we saw in the Vera-Rubin plot, it's a few kiloparsecs. That's a few tens or hundreds of light years. But that needs a very, very low particle mass. And there are many ways, actually, that we can look for evidence of wavelength of dark matter. And this is a summary figure, and I'm not going to explain everything on it. But we can use observations like black hole superradiance, the cosmic microwave background, reionization of the universe, dynamics of star clusters, the Lyman alpha forest, to try and constrain the mass of the dark matter if it's very low, and its contribution to the cosmic density. How does this work? By the Compton wavelength or the de Broglie wavelength. If the wavelength is smaller than the radius of a black hole, the Schwarzschild radius of a black hole with a solar mass, we will never be able to see the effect of the wavelength astrophysically. That's the smallest astrophysical object. Few kilometers of wavelength, radius of a black hole. If the wavelength is larger than the whole size of the universe, that's the Hubble radius today, then we can't see the wavelength of the particle because it's too big. But if the Compton wavelength is in between those two scales, we can try and look for evidence of the wavelength using the types of observations that I've indicated with these images. We can also, so this was trying to find the wavelength of the dark matter out in the cosmos, and that worked for very low masses. These masses 10 to the minus 10 electron volts to 10 to the minus 34 electron volts. If the dark matter is a bit heavier than that, we can still try and look for the evidence of the wavelength, but now evidence of the wavelength in an experiment on Earth. And that's using something called a microwave radio. So this type of dark matter, axion dark matter, if you apply a magnetic field to it, it will turn into a photon. So it interacts with magnetic fields. Dark matter comes in, hits a magnetic field, it will turn into a photon. And we can detect this process resonantly if the particle frequency, the frequency of the axion, matches the frequency of an antenna that we're using to try and detect the photon that it turns into. This is what such an axion microwave radio looks like. This is looking inside an experiment called Admx, which I'll explain on the next slide. But we're using the same resonance principle that the Jodrell Bank telescope uses. So this experiment has a resonance at some frequency set by its size. If that frequency matches the frequency of the dark matter, we can resonantly detect it. But we don't know the frequency of the dark matter. So you have to tune the radio. And in the case here, you tune the radio by moving these little rods. And it really is just like tuning your radio. If you're, say, on a car journey, or you're sitting at home listening to your radio, and you want to find a station, but you don't know the frequency. You don't know the frequency of the station you want to listen to. So you tune your radio, and you keep going until you find something that you like. But if you tune too quickly, you'll miss the station that you like. If you tune too slowly, you'll never get there. And your radio is also only sensitive to a range of frequencies, right? It's sensitive to like 88 FM to 106 FM. So you can't, and then you need a different radio if you want to listen to shortwave or long wave or medium wave radio. And the same is true here. We have to tune and wait to try and find the dark matter frequency. And this radio only works for a certain frequencies. So how do you generally detect these dark matter waves in a radio? Well, you need a magnetic field to turn the axion into a photon. You need a resonator, in this case a microwave. You need a fridge because you want to cool everything down, get rid of all of your background noise, because it's a very small signal. Remember, there's only 1 proton mass worth of dark matter in every centimeter cubed. So you need to really cool everything down and get rid of the background to detect this signal. And it's still a very tiny signal, so you need an amplifier to try and amplify that signal and work out whether you're seeing the dark matter. So the Admx axion haloscope does exactly that. So this is an image of this type of dark matter experiment. It's currently operating at the University of Washington in Seattle, and it has been for more than 20 years. And it has all the ingredients that we said. It has a magnet, it has a microwave cavity, it has refrigeration, and it has an amplifier, in this case, a superconducting quantum interference device. And you take all of these ingredients and you put them in a hole in the ground and you wait. And similar experiments are being constructed all over the world. And I want to make a comparison now between the search for axions and the search for a more famous dark matter candidate called the WIMP. Now, these are both historical dark matter theories proposed in the 1970s, 1980s, but they've had very different fortunes since. The WIMP is more famous. However, the WIMP is also much more strongly excluded. It's not ruled out, but it was strongly constrained. So here's the type of figure that you see if you hear people talk about WIMPs. So here we've got the WIMP mass, and the WIMP mass is around a giga-electron-volt at the same time as the mass of a proton. It's far too high to show up any wave-like effects, so we just think of WIMPs as particles, although of course they're both particles and waves. But the frequencies are too short, frequency's too high, wavelength's too long, just looks like a particle. We characterize it by its cross-section, the interaction cross-section, and we can try and search for WIMPs with a certain mass and cross-section. Now you make a theoretical prediction for where you think the WIMPs are if they compose a dark matter. And that's given by this red curve here. This is some prediction from supersymmetry for where WIMPs should be. Then you try and look for them by the collision of the particles with other particles in your detector, and you don't see it. And so you say, okay, here, by some experiment, for example, the Xenon 120 experiment excludes all of the WIMP models above the line. And the experiments have done very well. The theory makes a narrow prediction, and the experiments have done very well and have excluded quite a lot of the theory, although there's some that's still allowed. The case of the axion looks very different. It looks like this. So now again, I'm showing a kind of mass on the x-axis versus coupling, which is a kind of a measure of the cross-section on the y-axis. And again, I'm showing theory in red and exclusion in blue. But in this case, the theory is a line on this plot rather than a closed-in region. The theory is somewhat less precise, but it is there. There is a theoretical prediction. But the experiments don't do very well at excluding it, and that's because they have to work like radios. So here is the exclusion from Admx, and they have to tune their radio. And because they have to tune their radio, they can only search a small area. And also, because it's a radio, it only works at certain frequencies. They can only search here. So axions are very hard to search for, and we need many different types of technology to try and get from a picture like this to a picture like this, where we make an exclusion. So how do we do that? We need a different microwave. And an experiment that I work on, we replace that microwave with a topological insulator. So we take a type of crystal which has a resonant frequency and replace the microwave with the crystal. So I don't have time to tell you about that experiment, but that's my own contribution to what's going on here. But there are axion experiments with different types of microwave all over the world, and they've really sprung up in the last 10 years. We're trying to fill in that whole theory space around Admx with new types of radios. And they're all over the world. They're in South Korea, in Japan, in Europe, and Australia, and North America. And they have names like Admx, like Casper, like Abracadabra, like Organ. And these are just some of the experiments that I know of. And I've just made this map and put them on shortly before this talk, just to give you an idea of how this field is really at the forefront of dark matter searches in recent decades. And the future is bright. So if you take a projection for what that plot will change into, sorry for the change in color scheme, you go from Admx testing the theory to all of these experiments, Abracadabra, Admx, 2Rad, and we will cover almost the whole theoretical parameter space for the axion in the next 10 outside 20 years. So we will know if the dark matter is an axion with this original theory prediction. We will know. We will know in the next few decades. So it's a very exciting time to be studying this. And I'll close now. I'll finish now. So when is a dark matter particle a wave? And the answer is when the particle has very low mass. We can put a number on that. If the mass is between 10 to the minus 22 electron volts and 10 to the minus 3 electron volts, it will behave like a wave in a way that we can detect. On the very low side, 10 to the minus 22 electron volts, low mass means long wavelength in the de Broglie waves. If the wavelength is of order a kiloparsec, remember kiloparsecs is about the size of galaxies, Vera Rubin, this type of dark matter we call fuzzy dark matter. And it has interference patterns on the scale of galaxies that we can try and look for. And this is something that I've been interested in for many years. On the other side, if the mass is, say, 10 to the minus 3 electron volts, the frequency of the dark matter is terahertz, and in between going down to gigahertz, kilohertz. And if it has these kind of radio frequencies, we can search for it using radios, using axion radios of kind of general design. And there are many types of design out there. And Admx is this particular axion radio, and it works in frequencies of gigahertz, which are around this kind of mass scale. So that is the last thing that I wanted to tell you about. And thank you very much for listening. And if you want to find out more about axions, you can go to this free outreach article online. So I'll take some questions if there are.
Thank you, sir, for your wonderful lecture. Yeah, sir. So thank you for your wonderful lecture and a nice presentation. So if you allow, we can start discussion. We've got some question in inbox and in comments. So the first question, is there a relation between the neutrino and dark matter?
That's a very good question. So So neutrinos is like the first candidate you would think of for dark matter. They interact very weakly. They could be dark matter, and people pursued this idea for a very long time. But now we actually know that the neutrinos of the standard model, the neutrinos that we know exist, the electron neutrino, the muon neutrino, and the tau neutrino, they don't have the right properties to be dark matter. And the reason for that is that we know neutrinos have mass, and we know that they have a mass more than 0.06 electron volts, but less than about 1 electron volt. And in that range of masses that the neutrinos are allowed to have, based on experimental facts about neutrinos, they don't behave as dark matter should. In that range of masses, the neutrinos, well, first of all, there's not enough of them to be dark matter, and they're too light, they're too hot. They're produced in the early universe via the nuclear fusion reactions that make the hydrogen and helium, just like inside the sun. And they make neutrinos, and they come out hot. And because they're hot, they're moving too quickly to cluster inside galaxies, so it doesn't work. Now, you could take then something like a neutrino, say, let's take something like a neutrino, but make its mass heavier so that it does work like dark matter. And that is basically the idea of the WIMP that I said is a very leading dark matter candidate. It's basically a neutrino, but you make it heavier. It's called a neutralino. And it's a very popular theory, and it's been searched for a very long time. Hasn't been found. It could still be dark matter. It's actually very important. I don't want to say that WIMPs are a bad dark matter candidate. They're a very good dark matter candidate. They could still be the dark matter down here and below the lines where we've looked. So we need to carry on doing WIMP searches and build bigger, better WIMP detectors to try and search for them here. Because they could be dark matter, and they're very like neutrinos, and that's where the idea comes from.
Thank you, sir. We have another question. So, is dark matter responsible to eliminate antiparticle from the universe? So we know the asymmetry in particle-antiparticle. Mm-hmm. So, is the dark matter responsible for doing that?
Okay, yeah, that's another very good question. So, yeah, big mystery in the universe is why do we have matter and not equal amounts of matter and antimatter? This is problem called the problem of baryogenesis in cosmology, and you require an asymmetry to generate that. And axions are actually thought to could be related to this. So the symmetry that you need to violate to get matter instead of antimatter is called CP violation. It's the symmetry that is famous for Kabibo, Kobayashi, and Masakawa for their Nobel Prize, discovered that there is CP violation in weak interactions, but there's not enough to get matter over antimatter in the early universe. The axion is actually also involved in the puzzle of CP symmetry in the standard model. And if the axion in the early universe was doing something special, it could generate extra CP violation and help with the formation of matter over antimatter. Now, it doesn't. You can't do it, as far as I know, with this particular axion model, which is called the quantum chromodynamics axion. But axion-like particles, because of their relation to CP symmetry, could be involved in baryogenesis. I'm not an expert on that, but if you go on Google Scholar and like axion baryogenesis, there are many people who research this.
Thank you, sir. Now we have another question. So, can ordinary particles decay into dark matter?
Okay, excellent question. So, ordinary particles can interact with dark matter. They have to get the dark matter in the early universe, particularly in the case of WIMPs. So, in the case of WIMPs, to get the WIMPs in the early universe, what you do is you have an equilibrium between ordinary particles not decaying into dark matter but annihilating into dark matter, and an equilibrium between the dark matter annihilating into ordinary particles. And that's how you actually create the dark matter in the first place. So then you have to have that process. And that's how you can look for dark matter at the LHC. You take two protons. It's a rare process, but you take two protons, you hit them together. Sometimes they'll turn into two dark matter particles. You don't see the dark matter particles, so you infer you created dark matter. So that's a very good way to look for things like WIMPs at the LHC. It's also the case for axions. So when I said you can take an axion and hit it with a magnetic field, it will turn into a photon. That's not an axion decaying into a photon. That's an axion scattering off, if you like, a virtual photon and turning into a visible photon. But axions actually do also decay into two photons. So if you think of that as a Feynman diagram, where are we? Magnetic field, photon, axion, just turn it around a bit. Axion can decay into two photons, and that decay is very rare, but it can happen, and we do use it to try and search for axions. So if you have like a lump of axions out there in the cosmos, where we know they're there, say in a dwarf galaxy, they should be decaying very slowly into radio waves. So you can try and search for that process with radio telescopes. Radio telescopes like the Square Kilometre Array should be able to tell us something about the decay of axions into radio waves. So in both of these cases, you have interactions where you can turn dark matter into ordinary particles.
Thank you, sir, for your wonderful presentation and nice discussion. So we'd like to say thanks again on the behalf of the Department of Physics, Pabna, University of Science and Technology, sir, for accepting our invitation. We are very grateful to you for doing this webinar with you, sir. So I think our students have learned a lot of things about dark matter. So this may be the very good opportunity for them to interact with specialist physicists in dark matter like you. So I think it might be helpful for them in future, and maybe some of them may do their research in hand physics later. So thanks again.
Yeah, thank you.
Yeah, thanks again for
bye-bye then.
accepting. Yeah, bye for today. See you.